Okay, so welcome everyone to this year-long series of seminars at Acharya Pratishthan. This is the third trimester and this is the last month of the third trimester on the Calabi-Yau Threefolds. Today we have speakers, Professor Andrew Harder from Lehigh University. Andrew did his PhD in 2016 at University of Alberta with Professor Charles Doran. And after that, he was a postdoc fellow at Miami, and now he's assistant professor at Lehigh University. He has worked on the Calabi-Yau Threefolds and mirror symmetric aspect of it. Today, he is going to speak on the Calabi-Yau threefold coming from the hypergeometric family of K3 surfaces. So over to you, Andrew. Welcome.
Okay. Thank you very much. I really appreciate the invitation to speak here. Thank you to the organizers for inviting me, and thank you to all of you, both in the Zoom and I guess on YouTube where it's streaming, for coming to my talk. I appreciate all of that. So yeah, so I want to talk about some work that I did. Actually, this is, at this point, somewhat old work, I have to admit, with Chuck Doran under Novoseltsev and Alan Thompson. So I'm going to talk about various families of Calabi-Yau threefolds that you can construct from families of from a specific hypergeometric family of K3 surfaces. Okay, so let's start with a very broad question. So I want to talk about classification of Calabi-Yau threefolds to begin with. And so for me, a Calabi-Yau variety will be a smooth projective variety with trivial canonical bundles, so full stop. That'll be sort of my general working definition. But when I talk about Calabi-Yau threefolds, so three-dimensional Calabi-Yau varieties, I'm usually also going to assume that H10 is equal to 0. So for me, a Calabi-Yau threefold will have Hodge diamond 1, 0, 0, 0 with some A here, 1, B, B, 1, and then you have the obvious symmetries here. Okay, so when I say Calabi-Yau threefold, this is what I get. So I have zeros in these places. That's sort of the main thing. Okay. What I want to talk about largely is families of Calabi-Yau threefolds, or families of Calabi-Yau varieties. And so one thing that we know about Calabi-Yau varieties is that they have unobstructed deformations. In particular, the space of infinitesimal deformations of complex structures on a particular Calabi-Yau variety is of dimension H1 of the tangent bundle, the homomorphic tangent bundle. And since it's a Calabi-Yau variety, it's actually going to be equal to H1 of the dim x minus first wedge power of the homomorphic cotangent bundle. So in fact, this is a Hodge number. So this is dim x minus 1 of x. And so in the Hodge diamond that we saw before, that was in the, I can go back, it's just this Hodge number. Okay, so these are families of Calabi-Yau varieties, and just to give like a very basic example of a Calabi-Yau threefold and the Hodge number and the deformation space of it, we can look at smooth quintic hypersurfaces in P4. So by adjunction, such things are Calabi-Yau, right? So the degree is 5 and it's in P4. And the dimension of the space of quintic hypersurfaces, which is equal to this number here, is 9 choose 4 minus 5 squared, which is 101. Okay, so where's this number come from? So this is the number of polynomials of degree 5 in 5 variables. This is the number of different monomial deformations. And then you have a GL5 action on this. So I subtract the dimension of that GL5 group and I get the space of deformations. So a quick, easy computation of this. So this is generally the question that I want to answer. So once I know that families of Calabi-Yau varieties come in these nice deformation classes, I can ask questions about the classification of such things. So my first and very sort of straightforward question is how many deformation families of Calabi-Yau varieties are there? Or maybe a sub-question is how many diffeomorphism classes of Calabi-Yau varieties are there? So these are related, but not the same question. And so I can answer this in low dimensions in a very easy way. if I look at dimension 1, there's just a single family of Calabi-Yau varieties, which is elliptic curves, right? So this is why I don't want to claim that all Calabi-Yau varieties have H1 0 equals 0, because elliptic curves obviously don't. And obviously in dimension 2, there are two different deformation classes of Calabi-Yau varieties. We have abelian surfaces and K3 surfaces. So I guess when I say abelian surface, I kind of assume algebraicity, but I could also relax my definition of Calabi-Yau a little bit and just say, compact Kähler. And in that case, I'd replace this with complex tori. Okay, so I have various families of Calabi-Yau varieties. What happens in higher dimensions? So particularly, what happens if I look at Calabi-Yau threefolds, so three-dimensional Calabi-Yau varieties? The answer is that it's not even known whether there's a finite or infinite number of deformation classes of Calabi-Yau varieties. So it goes from a very well-known answer in dimensions 1 and 2 to completely unknown. This is a very interesting phenomenon. I don't quite understand it. So since the question of classification of Calabi-Yau threefolds in general is very difficult, we want to simplify our question and maybe specialize the classes of Calabi-Yau varieties that we're going to look at. So the question that I'll sort of follow this up with is, for a given type of Calabi-Yau varieties, how many deformation classes do we get? Or can we answer even the more coarse question of, is there a finite number or infinite number of Calabi-Yau varieties of a given type? So what do I mean by a type of Calabi-Yau variety? Let's give some examples of what I sort of mean by this. So the first example of classification or sort of boundedness results regarding Calabi-Yau varieties is due to Gross, and this goes back to the 90s, so Mark Gross in the 1990s, who proved that if I look at elliptically fibred Calabi-Yau threefolds, so these are threefolds which basically just admit a flat morphism to a surface. So if you have such a morphism, the fiber of the map is forced to be an elliptic curve. So the space of all Calabi-Yau threefolds which admit elliptic fibrations is bounded. So in particular, this means that there's a finite number of deformation classes, complex deformation classes of Calabi-Yau threefolds admitting elliptic fibration. Okay, and admitting elliptic fibration is a nice property, and it's a fairly common property actually among all Calabi-Yau threefolds. Generally speaking, if you have a Calabi-Yau threefold with big enough H11, most of the time, in my experience, they have elliptic fibration. So this is a pretty strong result. There are follow-up results by people whose names I forget about in higher dimensions, so not just threefolds, but I'm not, I forget who this is due to, so I'm not going to say anything more. I'll just mention that they exist. Okay, so this classification question is known. And then there's also similar results due to Kreutzer and Skark from around the same period, so the late 90s, early 2000s, I can't remember exactly when, which says that there are finitely many, and they, to some extent, enumerate. I'm going to give an approximation here, and I'll explain what this approximation means in a second. There's a finite number of Calabi-Yau threefolds, which are smooth hypersurfaces or generic hypersurfaces in toric weak Fano varieties. So what Kreutzer and Skark did was that they classified reflexive four-dimensional polytopes. So to each reflexive four-dimensional polytope, we get a Gorenstein toric Fano variety. And then inside a Gorenstein toric Fano variety, the anticanonical hypersurface is a singular Calabi-Yau threefold and such a thing. So what they proved is that there's 473 million reflexive-ish four-dimensional polytopes. So to each of these examples, if you take a maximal partial Krepin, anyway, a maximal Krepin resolution of these things, what you'll get is a not necessarily a smooth toric variety, but you'll get a smooth anticanonical divisor. And so for each of these cases, for each good enough resolution, you'll get a family of Calabi-Yau varieties. Sometimes there's redundancy, but sometimes for a given polytope, you get different Calabi-Yau varieties depending on the resolution that you take. So all told, this is, I guess, up to order of magnitude, roughly the number of Calabi-Yau threefolds that they were able to construct by their construction. Okay, so that classification is done. And then there is a nice follow-up result, which is much more recent. So this is like 2014 or 2016. I think 2014, the archive paper came out. This is by Borisov and Lee. And what they do is they show that for a given dimension, so say Calabi-Yau threefolds, there's only a finite number of deformation classes which appear as complete intersections in Fano varieties of a given type. So this basically is a consequence of boundedness results, of these big boundedness results that were obtained a little while back for Fano varieties. So this is, plus or minus some things. These are sort of the bigger results in the classification of Calabi-Yau varieties. I mean, there might be things that I'm missing, and I apologize if I am, but these are the big results that stand out to me. So coming back to my original question, the question is, so given a type of Calabi-Yau threefold, or a way to construct a Calabi-Yau threefold, if I have a construction, I want to show that the things that come out of that construction are finite, that there's a bounded family of such things. So these are two very nice constructions. There's elliptic vibration constructions and hypersurface constructions, or complete intersection. The question I can ask is, if I have other constructions of Calabi-Yau threefolds, do I get boundedness? So I want to introduce two different constructions of Calabi-Yau threefolds, or Calabi-Yau varieties, where I can sort of think about the same types of questions. So I'm gonna mention one and not really come back to it until the end of the talk, and then the next one I'm going to talk about a little bit more. So the first construction is a construction by Turin degeneration, or maybe smoothing. So by work of Kawamata Namakawa, or follow-up work by Namhoon Lee, we can construct a Calabi-Yau threefold by taking the following pieces of data. So if I take two threefolds, V1 and V2, so that I have a smooth anticanonical divisor S in both. So S is a K3 surface and it's smooth. So if I have some common smooth anticanonical divisor, I can essentially glue V1 and V2 along this thing and deform it under the condition that the tensor product of the normal bundles is trivial. So this is Friedman's essentially D semi-stability condition. Okay, so if I have these two things, what I get is I can construct a four-dimensional manifold, which is this X mapping to the complex disk delta, so that if I take the preimage of 0, I get the union of these two things glued along S. And if I take any other fiber, so T not equal to 0, the fiber is a smooth Calabi-Yau threefold, and this is unique up to deformation. So from such a pair, I can smooth and get a family, a deformation family of Calabi-Yau threefolds. So this is one very nice sort of class of Calabi-Yau threefolds that we can sort of construct starting from simpler pieces of data. And it's not hard to figure out what this data is. So the question, of course, is, can you show that there's a finite number of deformation families of Calabi-Yau threefolds obtained by this Turin degeneration or smoothing argument? So this is something I have not thought about too much, but I think it's something that's tractable. But it's sort of spiritually related to the question that I want to talk about a bit more, which is, and I'll explain why it's related. How do I classify Calabi-Yau threefolds which emit K3 surface vibrations? Right? So this is more related to the results of Gross that I mentioned earlier that say that there's a bounded family of elliptically fibered Calabi-Yau threefolds. So if instead of elliptic fibers, I ask for K3 fibers, so maps to a curve. So Calabi-Yau threefold is K3 fibered if it emits a surjective projective morphism to a curve. so that the generic fiber is a K3 surface, right? So actually, there's only two possibilities for generic fiber of such a surface. It can be a K3 surface, or it's going to be an abelian surface. It has to be Calabi-Yau. So the question is whether there are a finite number of families of Collabia threefolds admitting K3 fibrations. And it would be natural to expect that there's only finitely many, possibly sort of in relation to these results of Gross before, but also sort of largely because we know a lot about the moduli space of K3 surfaces, and this seems like a reasonable sort of expectation. So I'll say a little bit more about that in specific cases. So we can even simplify this question. So instead of saying, let's just classify or figure out how many families of Calabi-Yau threefolds there are that admit K3 fibrations over a curve, over a fixed curve, just any K3 surfaces, let's specify which types of K3 surfaces that we want, and see if we can answer that question in this baby case. So here's this question. So given a particular lattice, maybe of high rank, so we want to ask whether there's a finite number of K3 fibred Calabi-Yau threefolds whose fibers admit a lattice polarization by this lattice L. So I'll explain what these words mean in a little bit. Essentially what I'm saying is, not all K3 surfaces have the same number of curves inside of them, of algebraic curves. Some have more than others. So if I force my fibers to have lots of algebraic curves, that should sort of also restrict the class of Calabi-Yau threefolds that I'm looking at. And I want to classify those. So this is essentially the idea. And sort of the thing that I want to mention right at this point, so for us who are interested in hypergeometric differential equations and things like that, is that if the lattice is of rank 19 or in general, then we can actually use techniques coming from differential equations or data about various differential equations maybe to solve this problem. That's really sort of the thing I want to emphasize here. So we went from this very broad question, we specialized quite a bit, and now we have a much simpler question that can be answered using, and I'll explain this, data coming from ODEs. So this is sort of the thrust of the talk. Okay, so I want to say a little bit about K3 surfaces, but maybe I'll pause for a second if there are any questions or comments. Okay, so just to sort of, set up what I want to do, or the specific question that I want to look at, let's just remember what K3 surfaces are. So K3 surfaces are smooth projective surfaces, which are simply connected and have trivial anticanonical bundle. This is the definition I learned a long time ago from Noriko, who's in the audience. And so what do we know about K3 surfaces? Well, first of all, they're all diffeomorphic to one another. So the basic example of a K3 surface is a quartic hypersurface in P3. So all K3 surfaces are diffeomorphic to a quartic in P3, a smooth quartic. And so we know what their Betti numbers and Hodge numbers are. So in fact, the second Betti number is 22. And of course, this means that the Hodge diamond looks like 1, 0, 0, 1, 20, 1, 0, 0, 1. Okay, so that's what the Hodge diamond of a K3 surface looks like. We can also say a little bit about what the intersection pairing on the homology or cohomology of a K3 surface looks like. So the basic facts that we know are, well, we know the rank of H2. We know that it's even. This comes from various topological results. We know that it's unimodular just because it's essentially Poincare duality. And we know its signature, which is 319, by the Hodge index theorem. So as a consequence of this and the classification of even indefinite unimodular lattices, we see that the intersection pairing structure on H2 of a K3 surface gives us E8 squared, so twisted by -1, so there's a negative definite E8 lattice. So plus 3 copies of this U lattice, and the U lattice is just given by this graph matrix right here, right? So it's the unique, indefinite, unimodular, even lattice of rank 2. Okay, so we'll call this the K3 lattice. Once we have this, we can talk about the lattice spanned by algebraic cycles, which is the Picard lattice. So the Picard lattice is essentially for a K3 surface, the Néron-Severi group. And this is H11 intersected with the integral classes. And this is a lattice of signature given by one something. So that's what this is. This is by definition or by Hodge index there. We can also talk about, so I'll just make a comment that the Picard lattice must be of rank less than 20 because that's what H11 is. Okay. We can also talk about what's called the transcendental lattice of a K3 surface, and that's just the orthogonal complement of the Picard lattice. So these are sort of the most important two lattices that we'll be talking about here. And the Picard lattice is involved in what's called the lattice polarization. Okay, so to define a lattice polarization on a K3 surface, it's not that hard. It's basically just, you choose a lattice, a non-degenerate lattice with signature given by this, and I choose a K3 surface. So lattice polarization on this K3 surface is just a primitive embedding of this lattice L into the Picard group, so that the image contains an ample or maybe pseudo-ample class. Right, so all I'm saying is, choose some structure on this Picard lattice and just assume that it embeds into the Picard lattice of your K3. So for our basic example and for our most important example of the day, let's look at the family of mirror quartics. So these are hypersurfaces in P3 given by equations of the following type. Okay, I'm going to take t to be my parameter, and t is going to be non-zero or 1. And so these are very singular hypersurfaces. In fact, they have lots and lots of isolated ADE singularities. So when I take the resolution of such a thing, so I can smoothly resolve all members of this family at the same time. And once I do that, every time I blow up one of these singular points, I'm going to get an extra P1 inside of my my K3 surfaces. And so if you take the span of all those extra algebraic cycles, these P1s, plus the coordinate hyperplane classes, and you look at the intersection lattice that they span inside of the Picard group, what you get is called this lattice M2. So this is E8 squared plus U plus -4, or orthogonal sum. And maybe this notation makes more sense if I introduce Mn, which is E8 -1 squared plus U plus -2n. Right? So n is 2. And so this is a special case of this class of lattices that I'll call Mn. That won't come up later. It's just to explain why the notation is reasonable. Okay, so this is our basic family of lattice polarized K3 surfaces. So in each member of this family, we get a map from this M2 lattice into the Picard lattice. I should mention that this is not equal to the Picard lattice of all members of this family. In fact, there's a dense subset of C minus these 2 points at which the Picard lattice has rank 20, the maximal possible Picard rank of a K3 surface. This is just a fact, but sort of that being said, this dense subset is not open. So most points inside of this space, this family of K3 surfaces actually have Picard lattice equal to M2. Okay, so that's lattice polarization. And then we can talk about lattice polarization on a family of K3 surfaces, or of K3 surfaces. In fact, we can talk about lattice polarizations on a threefold. So I'll say that a K3 fibred threefold is L polarized if every smooth fiber of pi is L polarized. So if I take all the smooth fibers in this family, so I have a map going down from like some fiber space here to a curve C, and then I have like these fibers in here. So for each fiber, if I have a lattice polarization, and this lattice polarization is not sort of disturbed by monodromy, so there's always going to be a monodromy action on your Picard lattice, so the image of this L polarization. But if it's not disturbed by monodromy, then I'll say that the family is L polarized. So this is a very loose phrasing of the definition, but it's relatively straightforward. And so we have a very specific basic example that I think actually won't show up later, but I think it explains things fairly nicely, which is the family of mirror quintics. So mirror quintics are given by the following expression. This is, you'll notice that this is slightly different than my expression for mirror quartics. And I won't explain why they're called mirror quintics or mirror quartics. These are things that should appear in mirror symmetry as the mirrors to hypersurfaces in Pn. But anyway, so if you take a smooth resolution of this family, so this is the vanishing locus of this equation here, then each of these fibers, for each t, actually this should be lambda here, is fibred by mirror quartic surfaces. So you can sort of see this without taking the resolution, just by taking a pencil of hyperplane sections. So if you take this pencil of hyperplane sections, the base locus will be resolved under resolution, so you don't have to worry too much. And you can see that this is actually fibred by mirror quartic surfaces by taking these hyperplane sections. So if I take the hyperplanes given by this equation, I plug that in here. I think I maybe got some signs wrong in this equation, but maybe it should be a plus. But anyway, I'll leave that as it is. I plug that in, I get the family of hypersurfaces of this form. So for each lambda, I get a pencil of hypersurfaces in it that are just, if you go back to the equation before, the mirror quartics. And in fact, what you can see is that this is a pencil of mirror quartics obtained by base change from the mirror quartics. So I just move this to the denominator here, and I can see that that's actually what I get by taking the mirror quartic family, and for the parameter t, I plug in lambda times s5 over 1 plus s, because I got the sign wrong. Okay, so that's, we obtain these mirror quintics by base change from the family of mirror quartics. That's really the upshot here. Okay, so as a consequence of this, since the mirror quartics are a family of M2 polarized K3 surfaces, the mirror quintics admit K3 surface vibrations, which is M2 polarized. Okay. And so now we've arrived at the actual question that I want to answer, which is, how do I classify all M2 polarized K3 fibred Calabi-Yau threefolds? So I've gone from an extremely broad question that I think is hard to solve to something that's easy and that will involve a very specific hypergeometric ODE. Okay. Any questions at this point? Comments? Okay. Okay, so before I talk about the answer to this question, I want to talk a little bit about the moduli of lattice polarized K3 surfaces. So this will be sort of an important invariant in this classification, so I'll mention what these things are. So if I want to talk about classifying K3 fiber things, I should first talk about the classification of those K3 fibers. And that's what this moduli of L polarized K3 surfaces does. So the moduli space of pairs consisting of a lattice polarization and a K3 surface is given by an arithmetic quotient, which is this moduli space ML, or period space, which is some homogeneous space PL modulo group gamma L. In particular, what is this? In particular, what I should do is I should take a component of the space of pairs of the following things. So I take the projective space of the orthogonal complement of the image of this embedding. So I take that and I tensor with C. So that's a complex projective space of dimension equal to the dimension of the transcendental lattice of this lattice polarized K3 surface. Then I take the quadric inside of that, determined by the vanishing of this equation. And I take the piece of this quadric so that Z and Z bar have pairing greater than 0. And then I take a single component of this. So this usually has two distinct path connected components. And I just take one of those for the sake of simplicity. And in the particular case where the lattice is M2, what this turns out to be is just the standard upper half space. So the group that I'm interested in is gamma L. This is the image of a particular map inside of the orthogonal group of L perp. I should actually maybe have written an I L perp here. So I take those elements in the orthogonal group of the K3 lattice, so that when I restrict to the lattice L, or the image of L, I get the identity. So things that just fix the lattice, the image of iota in this, under this map. Okay, so I take that, and then I take the natural projection onto the orthogonal group of L perp. And in the case where L is M2 lattice, what this turns out to be is something that's just isomorphic to gamma naught of 2 plus. So the standard modular group with the Atkin-Lehner involution added. So then I just take the quotient to get my moduli space or period space of K3 surfaces. And this turns out just to be, in our case, just a standard modular curve. So something that I think most people are fairly familiar with, certainly if anyone's in this audience. Okay, so now we can use this as sort of an invariant of a lattice polaris K through fibred threefold. So what we get is anytime we have a lattice polaris K through fibred threefold, we get a period map from the base curve of the K3 fibration to the compactification. So this is the Bailey-Borel compactification of the moduli space. So in our case, the compactification here is just P1, right? Because that's the compactification of this thing. So in fact, this space is P1 minus 3 points. I can just say 0, 1, and infinity. And so this is just P1. Okay.
What is positive sign representing here?
The positive sign means I add the Atkin-Lehner involution. So that you take this group and you just add one more square, square, order 2L. Okay. Great. Okay, so let's move on. So here now we come to basically lead up to the main theorem that I want to talk about. So the first theorem, and this is the engine that makes this all tick, sort of, is that if I have an M2 polarized K3 fibred threefold, so of any type, it doesn't matter whether this is Calabi-Yau or whatever, then this threefold is determined up to birational transformation by its period map. So this is something specific to the M2 lattice. So knowing what this thing is tells me exactly up to birational transformation what X is. And okay, so since this is a moduli space of M2 polarized K3 surfaces, this might be either obviously true or obviously false, depending on your perspective. But it's actually true in this case. So if I, instead of this, done the sort of same thing with elliptically fibered surfaces, then this would not be true. Right? So the period map of an elliptic fibration doesn't determine the elliptic fibration. It determines it up to, choice of monodromy representation. But in this case, since there's sort of particularities with respect to the monodromy representation that mean that this is actually true here. So we can actually determine the Calabi-Yau threefold or the threefold in general by this map. And moreover, we can use the mirror quartic family to say something about how to actually reconstruct it. So not only do we have this theoretical result about period map determining threefold, we have a result about how to geometrically get back to where we started from. So this says that for since the period map of the mirror quartic family is an isomorphism, this is something that is checked. Any M2 polarized K3 fibred threefold is obtained up to birational transformation by base change from the mirror quartic family. So really what I should have here is I should have drawn this period map. I take a pullback of Y, and then I have a birational isomorphism to any X. So there's always such a birational map. So that's really the statement. And this is something that we already sort of saw in the case of mirror Quintix. So we exhibited a K3 fibered, a K3 fibration on these mirror Quintix. And we really saw from the little computation that we did that this K3 fibration is obtained by pullback from mirror quartics. And it was by the map, which was, I think, s to the 5th, lambda s to the 5th over s plus 1. Right, so that was the map, that was the period map for the mirror quartics. So this depends on the parameter lambda. It was a one-dimensional family of mirror quintics. And this was the. So in practice, these are very tangible, down-to-earth things that we're dealing with here. Okay, so this leads us to the following main theorem. The theorem that I want to talk about today. It says that if I have an M2 polarized K3 fibred threefold, then I have necessary conditions in order for X to be Calabi-Yau. So the first condition is actually a general necessity for any Collabia with a K3 fibration. Is that the base curve must be P1. And so this is just a very basic consequence of the Leray spectral sequence, along with the fact that H01 of X is 0. There's nothing complicated going on here. That's just a general fact. The second thing is much more interesting, is one of two conditions. So the first one is really the most important. So it's that the period map, so there's a map which goes from P1 to P1. And this has 3 special points given by the points that we added back to compactify the moduli space to P1. And this contains P1 minus, there are 3 special points, 0, 1, and infinity. So there must always be 2 points in the preimage of infinity, which are denoted y1 and y2. And the ramification indices of these points must be 1, 2, or 4. So that's very precise. There's another sort of subcase that can happen here, which is that if I have ramification index 1 and in fact things collide. So there's a subcase here that I won't say too much about. It's sort of less important and sort of is contained in the other situations. Okay, so these are necessary conditions for X to be Calabi-Yau, just based on the period map. And there's a second part to this theorem, which is a bit more difficult, or uses different tools, I should say, which says that for any map from P1 to P1, which satisfying the conditions above, okay, there is an actual M2 polarized K3 fibred Collabia threefold, whose period map is G. However, we have to give something up in general. So if there's ramification, it can be possibly singular if there is ramification over the point 1. So under certain conditions, you can have slight singularities, but this is minor. We should put this off to the side. So this is the statement at the end. So if there's ramification over the point 1, then this actually admits a smooth model. So we get our really precise classification of M2 polarized K3 fibred threefolds. Okay, that's the point here. Okay, so this is the main theorem. I want to say a little bit about how it's proved, though I think I'll skip some of the details that I prepared to talk about for the purpose of time. Are there any questions here? Okay. So in order to say something about the proof, I need to know what a variation of Hodge structure is. So I want to use differential equations to prove the first part of this theorem. So I need to know a little bit about what this differential equation will tell us. It's Picard-Fuchs equation inside of the family of K3 surfaces. So a variation of Hodge structure has a local system and a flat connection, so the standard flat connection, so that the kernel of this flat connection is our local system tensor with C. In addition, we want a filtration on the tensor product of this local system with O of U, which satisfies Griffith's transversality. So I'm going to go a little quick here. Hopefully people know this stuff. And I also want that on each fiber, the restriction of this filtration here, along with the vector space here and the rational structure that I get from the local system, that this forms a pure Hodge structure. So that's what a variation of Hodge structure is, very briefly. Once I have a variation of Hodge structure on a curve C, and so if I have a variation of Hodge structure, so usually variation of Hodge structure will exist on just a quasi-projective variety, and you can't usually push it onto a compactification of that quasi-projective variety. What the quasi-canonical extension does is tells you how to, a nice way at least, of pushing forward part of the data of a variation of Hodge structure to a compactification. So the local system usually won't push forward into a compactification of your variety. So given a variation of Hodge structure on some open subset in a curve C, we can always extend the line bundles in a variation of Hodge structure to line bundles or vector bundles, sorry, on C in a nice way. So first of all, we want these to extend to a filtration, and that's going to happen. So this is what we're guaranteed here. And then we'll define these Hodge bundles to be the quotient bundles of these extensions. And we also extend the connection nabla to a logarithmic connection on all of C. So this is all stuff that's guaranteed to us by Doran, and done in sort of a nice way. See, and it tells you sort of how this Hodge data extends. So these are important players in what I have to say later on. So I thought it was important to say a little bit about this. Okay, so once we have all this, we have a theorem of Sucker, and I guess after that Saito, which tells us that if we have a local system on the open part of a curve, and this underlies a variation of Hodge structure, then when I take the push forward, so this push forward is J, U going to C. So if I take this push forward and I take its cohomology, H1 I wrote, and in fact, oh, I wrote H at, good. This carries a pure Hodge structure itself. So the Hodge structure on the cohomology of this push forward local system itself admits a pure Hodge structure. So the example of variation of Hodge structure that always appears is when I have a smooth morphism from a projective variety Y or quasi-projective variety, smooth projective morphism, to a curve or to some space U. So we always get a variation of Hodge structure on the cohomology bundle. So the fibers of this cohomology local system are the cohomology of the fibers of this map pi. And the underlying pure Hodge structure gives us this filtration in bundles just by taking the filtration on each fiber of this local system. Okay, so there's a standard way of doing this, and this is sort of our main example of variation of Hodge structure. And one thing that Zucker proved is that, okay, so if I have a map Y to U, I can compactify Y bar to a smooth projective. So what Zucker proved was that the canonical Hodge structure on the push forward of the local system on this part here, so this is our pi, this is compatible with the Hodge structure on Y bar by the array spectral sequence. So in fact, this is a direct summand of H n of Y as a Hodge structure. Okay, so I can tell something about the Hodge structure of a compactification of fiber space over a smooth curve just by looking at something about the cohomology of the local system controlling smooth fibers. So the question, of course, that I ask is, can I determine whether morphism from X to P1 is Calabi-Yau, whether this variety is Calabi-Yau, just using the structure of the local system or this variation of Hodge structure coming from that? So that's the question. So can I use like just data about the smooth fibers of this variation of Hodge structure to find out whether something's Calabi-Yau? And the answer, of course, I ask questions, the answer is yes, is the following thing. So maybe I won't go into this. Maybe I'll just sort of go through this pretty quickly. It's this proposition, which is essentially a theorem of Delangelo, Mueller-Stack, Van Straten, and Zwolle, which says that if I have a Calabi-Yau, then I must have that H1 of the E02. So this is one of the Hodge bundles that I introduced earlier. This is F0 mod F1. That this must be equal to 1. So in fact, what this says is that this is O of -2. Right, so it tells me exactly something about the degree of a particular Hodge bundle. So, right, so I'm not going to go too much into the proof of this. I have it written down briefly here. It doesn't really take much effort, and the heavy lifting is really done by this theorem here. And so I'll leave it at that. So for the sake of time, I'll just leave it there. So we can then use a theorem of Eskin, Kinsevich, Muller, and Sorich to compute the degree of E02 from the Picard-Fuchs equation of the smooth part of my K3 fibred threefold. So I have a map to P1, and then there's an open subset U inside of here and an X0 inside of here, so that this is a smooth morphism. So I want to use the Picard-Fuchs equation attached to the smooth part of this morphism to compute the degree of E02. So just to say quickly what the Picard-Fuchs equation of a family of varieties or K3 surfaces is. So it's the following piece of data. So let's assume that I have a smooth family of K3 surfaces, and that I choose some sigma, which is a relative canonical section, relative differential two-form on my fibers. So choose a two-form. Then I have a pairing between this sheaf and the homology sheaf going to space of functions on the base. And this will take a pair consisting of my form and a local homology section on my fibers, just to the integral. I mean, maybe more precisely, these are just periods, local periods of the family of K3s. So if I take the multi-valued functions that I get, which I'll call G tau, so these are sigma paired with tau on U, these can be viewed as the set of solutions of a specific differential equation, which I'll call the Picard-Fuchs ODE of the pair X0 and sigma. So these depend on the choice of holomorphic form that I made, but the results that'll follow don't make any reference to that. So I get a Picard-Fuchs equation for a family of K3 surfaces. And then I can use that Picard-Fuchs equation to determine the degree of E02. So I'll make some comments about what exactly the process to do this looks like. And it takes a couple different pieces of notation that I'll mention. So first of all, we use what's called the parabolic degree of these Hodge bundles. So the parabolic degree is just the actual degree of these bundles with some extra stuff which can be computed from the Picard-Fuchs equation. So the nice thing about this parabolic degree, which is defined by Simpson, is that it satisfies this nice sort of duality statement that EPQ has the same parabolic degree as EQP -1 times -1. And in particular, for us, the important part is that this says that E11 has 0 parabolic degree. So in fact, if I look at this, this means that the actual degree of E11 can be computed from stuff which is computable from the Picard-Fuchs equation. So that's our first important fact. And second, we have maps between each EI, EJ. So what I'll get is I'll get a map from E1 to E02. I'll know this degree, and I want to know what the co-kernel of this map looks like so I can compute the degree of E02. That's really the tactic here. And so the idea is like, so what is the co-kernel of that map? I mean, the co-kernel is determined by this following theorem of Eskin, Kinsevich, Muller, and Sorich. So it says that if I have any variation of Hodge structure on P1 minus some points, so that the rank of each of these Hodge bundles is 1. So that this is going to be satisfied in the cases that we're interested in. Then I can compute the co-kernel of the Kodaira-Spencer maps here that I got from this data. So these are just extensions of the Griffiths of the Gauss-Menin connection. These are just so what the Gauss-Menin connection does to these Hodge bundles. Okay, so it tells us that if I have an apparent singularity, and it tells me how to do this in terms of the characteristic exponents of the Picard-Fuchs equation. Right, so it tells me how to do this. That's really the important part. This theorem tells me how to compute this Kodaira-Spencer map with a co-kernel of that using Picard-Fuchs equations. So it tells me that if I have an apparent singularity in my Picard-Fuchs equation, then the co-kernel has length given by this difference of characteristic exponents. So if it's an apparent singularity, it has integral characteristic exponents, so this makes sense. If I have an actual singularity, then the co-kernel is given by some formula involving the floor function of these characteristic exponents, which, you know, they can be integers, but they can also be rational numbers. Okay, great. So this tells me how to compute the co-kernel. So the tactic now is to compute whether something is Calabi-Yau. I want to compute whether the degree of E02 is -2 or not. So I compute the Picard-Fuchs equation internally for each family of Calabi-Yau threefolds that I'm interested in. I use things like the local monodromy matrices to compute, and this is stuff that can be just extracted from the Picard-Fuchs equation and its local exponents and things like this, or characteristic exponents and things like this, to determine the difference between the parabolic degree and the actual degree for both the E02 bundle and E11. Then I use the fact that the parabolic degree of E11 is 0, and the theorem that I listed on the previous slide to compute the degree of E02. So that's the tactic. So we put all this together and we sort of see that we can actually compute everything. So to give a very basic example and to explain where, you know, my connection to hypergeometric things comes in, let's try to compute let's try to do this computation for the mirror quartic family. Okay, so for the mirror quartic family, the Picard-Fuchs equation is this hypergeometric type equation given by this. Okay. Very standard, straightforward, and of course delta is just t d dt. Okay, I can then compute the local monodromy matrices at the 3 points of interest, and I get this maximal unipotent matrix at 0. I get this order 4 matrix at infinity, and I get this order 2 matrix at 1. Right, so this is a conifold monodromy, and this is a sort of an orbifold type thing here. Okay, so from these monodromy matrices, I didn't tell you how, but you can compute the parabolic degree. So the parabolic degree takes one contribution from each singular point here, from each non-trivial monodromy, and I put something in there, and then I get the sum of those contributions plus the actual degree, and it turns out to be these equations here. So so this one doesn't really matter, I don't really care about that one, but what I really care about is this line and this line. So in this line, what this tells us is that the actual degree of E11 is -1. And this tells us, well, the difference between the parabolic degree and degree of this. Then I can use the characteristic exponents of my this Picard-Fuchs equation to try to get the co-kernel, the length of the co-kernel of the Kodaira-Spencer maps. So that'll give me something here. And I do this computation as I see here, and I find that the length of this co-kernel is 1. Consequently, the degree of E02 is 0. So H1 of the trivial bundle on trivial line bundle on P1, of course, is 0, and that tells me that H30 of the mirror quartic family is 0. Okay, so this is something, so it's not Collabia. This cannot be Calabi-Yau because for any Calabi-Yau, I have H30 equals 1. Okay. This is something that's sort of obvious because the mirror quartic families have pencil hypersurfaces in projective space. So of course, the total space of that thing must have H30 equals 1. But the important part of this is that it gives us a general strategy for proving sort of the main theorem that we have here. So we can apply the same technique. And in fact, we use the computation that we had on the previous page to prove the general statement. And we basically use the following idea. So we know that any M2 polarized K3 fibred threefold can be obtained from the mirror quartic family by base change along the period map. This was a statement that we had before, and I'm just restating it. So this means that the Picard-Fuchs equation of any M2 polarized K3 fibred threefold can be obtained from the hypergeometric equation that we had on the previous page by base change. So we can just sort of pull that back along the map and get the internal Picard-Fuchs equation for any family of M2 polarized K3 surfaces. This also means that I can compute the local exponents and local monodromy and all the parabolic degrees and all the lengths of the co-kernels of the Kadair-Spencer maps from the period map plus the data that we had on the previous page. So we can compute all the important parts for computing the degree of E02 just by using the map and the period map and the hypergeometric ODE we had before. So we can just apply the same amount analysis as that we had to get the classification result that I talked about earlier. So it's really just computation before plus some data about the map, and there you go. It all sort of pops out of there. Okay. So any questions about this? Okay. So where am I at in terms of when I should stop and things like that? Should I stop soon? Do I have 2 or 3 more minutes, or how's this going?
If it is over, you can stop. And let's thanks Andrew for the wonderful talk. If it is over.
Okay. Sure.
And if anyone has any questions. It seems no. So are there people studying in the one parameter family? Are there more equations which are not hypergeometric also?
Pardon me, I don't think I understood.
With moduli space being dimension 1, are there Calabi-Yau threefolds which are not hypergeometric?
Yeah, there's lots. So you can even construct some from this construction. If you take a family of maps with sort of specialized, I can say something about space. So maybe I won't say too much, but you can definitely do that even from this construction. There's lots of families that are not hypergeometric. Yeah.
I see. And another related question, if the dimension is not 1, are there hypergeometric families which are studied?
I don't know actually any, I mean, I'm sure there are. I don't know anything about higher dimensional hypergeometric families of Calabi-Yau threefolds. I know there's lots of hypergeometric type Calabi-Yau families of
No,
K3
I'm asking if
surfaces.
moduli space is dimension more than 1. Calabi-Yau threefolds.
Yeah, I don't know of any. I mean, perhaps they exist, but I mean, there's obviously like GKZ type things that appear describing families of Calabi-Yau threefolds. Those are, I guess, spiritually hypergeometric. Those are relatively common, but I don't know of any like classical things that appear like hypergeometric families of Collabia threefolds.
And one general question: how people in string theory uses these recent results? Are they important in the string theory also?
Are these results useful in string theory?
Yeah, I mean, this development in the last 10 years on this one parameter family of 14 manifolds.
Mm-hmm.
So what are the string theory consequences of this?
I don't think I can say too much as to like specific string theory, but in terms of, I mean, so from my perspective, I guess, you know, these appear largely as things inside of mirror symmetry. And so mirror symmetry is, I guess, in its history, a duality between different types of string theory. And there have been lots and lots of developments in mirror symmetry in the last couple of decades or so, basically improving various versions of a homological mirror symmetry. Whether if I'm a physicist, I care about that or not, that's kind of a question. So I mean, these are certainly, you know, sort of the Calabi-Yaus and their invariants are really the part of the basic data of string theory. So from that perspective, it's interesting. I don't know. Did that answer the question at all?
Yeah, a little bit.
Okay.
Okay. Thanks then. So
Okay. Thank you very much
for this wonderful talk, and I think it will be important in the whole program. So we will close the session now.
Okay.
And see you sometime again. Bye.
Okay. Bye.